So we're talking about spring problems right now, and I'm going to work 3 more problems here that have variable geometry. In other words, you don't know what the final position of the spring is going to be, and it's part of the solution. And so the easiest example of that is a right triangle. And so if I have a picture that looks like this, of a spring that has some length L, and it's attached to a pin here and a roller here, and I apply a weight W to this roller. And so this roller is constrained to move vertically. This horizontal distance is a given number D. But as this weight falls, the spring stretches. And at some point, this system is going to reach static equilibrium, and we can find that position, or we should be able to. So the given numbers we're going to be given is, and I'm going to assume that the unstretched length of the spring is D. It doesn't have to be, you can do it differently, but that's, so L naught is equal to D, spring constant K, weight W. So this is what you're given. If you draw a free body diagram of this weight here at an arbitrary position, you've got a spring force, Fs, at an angle theta, which is equal to this theta. You've got a force in the slot, so you've got a P force, and then you've got the applied weight hanging down. When this reaches an equilibrium position, this is the free body diagram. So I can write 2 equations of equilibrium. I can sum forces in the x direction. So I have Fs cosine theta minus P is equal to 0. And in the vertical direction, I can write Fs sine theta minus W is equal to 0. Well, these are 2 equations. But if you look at the unknowns, I know W, but I do not know P, I do not know Fs, and I do not know theta. So I have 3 unknowns. So somewhere I need a 3rd equation. And so from the spring equation, Fs is equal to a spring constant times stretch. And the stretch is L, the current length L, minus the unstretched length, which is D. But just looking at this triangle, L times cosine of theta is equal to D. And so L is equal to D over cosine theta. And so I can plug in a D over cosine theta for L. And there's a D here, and so I can factor out a D. And so I'm left with an Fs is equal to spring constant times D times 1 over cosine theta minus 1. And so this gives me 3 equations that I can solve for 3 unknowns, Fs, P, and theta. Unfortunately, these equations are nonlinear. And so I can't do a simple matrix solution of them. And then you basically have 2 options that I know of. And one is to put this into an Excel program and do an iteration using the solver in Excel. And I'll do that in a separate video, show you how to do that. And for these sample numbers, for D is equal to 3 feet, K is equal to 50 pounds per foot, and W is equal to 20 pounds. If you iterate on these equations, and you can do that in Excel, we get an angle of about 35.6 degrees. My slot force, normal to a slot force, is 28 pounds, and my Fs spring constant is 34.4 pounds. And you can calculate the stretch too. And so from this theta, you can get L, and then you can get stretch for this set of numbers. So you're solving a nonlinear set of equations. You can also do these on your TI nSpire. You can actually go to, I've not told you to go there, but you can go to Menu, Algebra, Solve System of Equations. The second one, Solve System of Linear Equations, that takes you to Simult, but I've just told you to go straight to there. But the Solve System of Equations 1 is basically for nonlinear equations. And so you can go enter, and it says how many equations are you going to enter, and you can say 3. And the variables, you can go X, Y, Z. And what I did is I changed these variables. I let fx equal x, I let theta equal y, and I let p equal z. And so I rewrote these equations in terms of x, y, and z. And so you can go OK. And now it gives you this solve template. And you can actually write your equation. So you can write x, let me move up here so you can see better. You can write x times cosine y minus z equal 0. That's your first equation. The next equation is x times trig sine of y minus 20 is equal to 0. And the third equation is x minus 150 times parentheses 1 divided by cosine y minus 1. Step out of the parentheses, and that's equal to 0. And so this is using its solve function, and you should be able to hit enter. And I believe it's an iterative calculation. And it gives you several solutions. But if you have to kind of sort through the solutions and see. But the correct one is Z is 28 degrees, or 28 pounds. Y is so X is 34.39 pounds, Y is 35.56, and Z is 27 pounds. And so you can actually use the nSpire to solve this nonlinear system of equations. In a separate video, I'll show you how to do that in Excel. And so that's this problem. Not easy. But basically, you're writing equations that define the system. Free-body diagram, equations, spring equation. 3 equations, 3 unknowns. And so it's classical engineering, systems analysis, writing equations that define the system. If they're linear equations, you can do a simple matrix analysis. If they're a nonlinear set of equations like these, then you have to use an iterative method, or, which is basically the nSpire is using an iterative method too. And again, I'll show you in Excel how to do this in a separate video. So that's this problem.